Okay, so the one and only example we are going to look at for two-dimensional conservation of momentum, and I say only example, you will understand why when we're done at the end of this. Please try not to hate me as we go through all of this. The equations get long, but we're going to look at an example just so you can kind of see. The application is the same as what we've looked at for kinematics. There's just more components. But it's the same concept. I'm going to split them into horizontal and vertical components because momentum is a vector, because velocity is a vector. I need to consider the components. I can only add directions to each other. I can only add x to x and y to y. So it matters. I need to break it down into components. I'm going to use Fidessa to solve this, though. So first, let's read the problem. A hockey puck of mass 0.17 kilograms, and that's actually fairly accurate for their actual mass, travels at a velocity of 20 meters per second at 30 degrees. So that's written in polar coordinates. I do the radius and the angle. That tells me the magnitude and the direction. Collides with an unknown object of mass 0.5, so something heavier, traveling at a velocity of 10 meters per second and at 80 degrees. So they're both traveling relatively in the first quadrant direction. If the hockey puck travels 14 meters per second at an angle of 140 degrees after the collision, what is the final magnitude and direction of the velocity of the unknown object? All right, so the thing that we are looking to find is the final velocity of whatever our unknown object is. I'm going to call it V, U for unknown, F for final. Just, you can pick whatever subscripts you want to pick for that. I, our image, draw our hockey puck. We'll call this H. It's traveling 3 degrees is more realistically about there. We'll call this V, H, I, the initial hockey puck velocity. It's going to collide with some unknown object. Oof, unknown object's bigger. You can see how bad I am with circles. We'll call this U. It's traveling about 80 degrees. It's about not quite 90 degrees. So this is V, we'll say U, I, little arrow above to denote its velocity. That's roughly a good idea in terms of image, just so I can kind of picture what they're doing. Our D for our data points, I have V, H, I. I'm going to write this just in terms of the magnitude, and then I'll write the direction as a separate data point. So this is 20 meters per second. This will be U, H, I. This is going to be 30 degrees. I have V, H final as 14 meters per second. That's the hockey puck's final velocity. The angle or direction for the hockey puck, the final angle is 140 degrees. The mass of the hockey puck is 0.17 kilogram. All right, the unknown initial velocity is 10 meters per second. The unknown initial direction is 80 degrees. And well, let's write it up here because we're going to need the space. The unknown mass is 0.5 kilograms. And again, because I know we need the space, I make these really small so we can kind of see them there. So those are my data points. The equations I am going to use. Now, I could include the trig equations. I don't really require that, but so long as we remember that the cosine of an angle is adjacent over hypotenuse, that corresponds to our x component. The sine is opposite over hypotenuse, that corresponds to our y component. I remember that, then I'm good. Then the other really only equations I need are that momentum is going to be conserved. Now, this example is either one of two collisions. We talked about the types of collisions from the previous examples. One collision, it could be, is a perfect elastic collision. I'd need to prove that with energy. I'm not going to require you guys to do that yet. Or it could be an inelastic collision. The key is they're going to collide and then they're going to separate. So it's either perfect elastic or inelastic collision based off of the calculations that we do, which again, we're not going to go through. The math and how we find the momentum and the velocity is going to be the same either way. So momentum is still being conserved. The equations then are the change in momentum is going to equal 0. The momentum is equal to the mass times the velocity. For a perfectly elastic or inelastic collision, the momentum before is the momentum of one of the objects. In this case, we could do 1 plus the momentum of 2, and it's going to equal the moment, so we could call it initial. Initial is the momentum of 1 final plus the momentum of 2 final. That's just a weird abstract way to say they are separate before, they stay separate after. So then let's go to actually writing out the solutions for this. And the way I'm going to do this is I'm going to do the change in momentum for our x direction. Let's just do the horizontal momentum components. I'm going to write them all out because, again, we're going to really need the space. The mass of the hockey puck, the velocity, the initial velocity of the hockey puck in the x direction. So that's going to be the velocity of the hockey puck initial times the cosine of its initial angle, which I have here at 30 degrees. I'm just going to put a HI. Because if I'm solving it symbolically, I only plug in numbers at the end. So we're being true to Fidessa, but you can tell why maybe I don't want to do Fidessa for this problem. So that's the initial momentum in the x direction of the hockey puck, plus the mass of the unknown object, the initial momentum of the unknown object, the cosine of its angle, and that's its x-directed momentum, has to equal, by conservation of momentum, their corresponding final momentums. So in this case, this is the mass of the hockey puck. It has not changed. It's not losing mass. The final velocity of the hockey puck and its final angle position, plus the mass of the unknown object, the final velocity of the unknown object, which is something I don't know. That's what I'm going to be finding. And the angle of the unknown object, its final velocity, which also I don't know. That's going to be my x-directed momentum. I'm going to solve this equation for this component right here. So I can do that by subtracting this to the other side and then dividing mu through everything. I'm going to kind of do this quickly, but you can pause the video to stop and check it on your own. But because there's a lot of equations in this, I'm going to do it kind of quickly. When I just algebraically manipulate it, I solve for VUF cosine theta UF, the horizontal velocity of the unknown object, I get this big old yucky expression. I can do the same thing for the change in y. I'm going to note real quickly here so you don't feel like you have to do so much extra work for this. This is actually the exact same equation except for with one variation. Instead of having cosines, or wherever I have cosines, I just have sines. So its setup is exactly the same. The manipulation is exactly the same. And again, I know I'm going kind of quick here, but again, you understand why. You already see how long that equation is. The y component velocity then looks like. So we now have this really long expression for the y component of the vertical velocity, final velocity for the unknown object. Yuck. Right? So the way I'm going to essentially solve for, I'm going to solve for the angle first. I'm going to solve for the angle by taking the vertical component of the velocity and dividing it by the horizontal component. So I'll get sine over cosine, which is going to give me tangent. So already see we've got a lot going on here. Again, why we're only looking at one example. On the right or on the left-hand side, some of my things cancel out. These two terms cancel out. If I get sine over cosine, that is the definition of tangent. And I can't simply cancel out the right-hand side, so I am going to just leave it the way it is. But what I end up getting is I get the tangent of the final angle is equal to these big expressions or this big fraction. And then if I take the arctangent, I get the actual angle. So the arctangent gives me the angle. I get, essentially, I'm just simplify this a bit and arctangent both sides. I can't cancel out the mass ratios right here because it's not distributed to every term. So this is actually as simplified as it gets. And this would be the answer to one of the solutions. Like if I were doing this for a homework problem, this would be one of the solutions I would box, which is not why I'm going to give you one of these. Yuck. Before we plug everything in, let's talk about what because this just gives us the direction of the velocity. Let's talk about what the magnitude of the velocity would be. And I'm going to use Pythagorean's theorem to evaluate the magnitude of the velocity. The magnitude of the velocity, the u final, is going to be the sum of the squared rooted sum of the squares, right? So this is vu final x squared plus VU final y squared. And I'm actually going to leave this as my solution for this problem set as well, because what is the numerator for my angular component? Well, that was the entire y component of my velocity. That is what that angle is, or that is what the numerator is. So my numerator, let's do this and maybe we can highlight or match the colors so you can kind of see what I'm talking about here. This is my numerator. So when I solve for the angle, I'm going to just solve for the numerator first. Then I'm going to solve for the denominator, and then I'm going to plug it in the arctangent. But the reason I'm going to do that is because if I solve for the numerator first, I can then have it as an answer for the second part, find the magnitude. So this is then my denominator, that's my x component. So let's plug in, that's the rest for our solution set. Let's actually plug in for our answers. And again, you can see I'm speeding things up here a bit because it's long, but you can see I get, essentially I'm taking the arctangent of what would be 10.188 divided by 11.272, and that gives me 42 degrees. Now, when I put in my VU final, I'm going to get, essentially this is going to be 10.188 squared plus 11.272 squared. And that's going to give me about 15.19 meters per second. So those would be my two answers for a two-dimensional conservation of momentum problem. And again, which now you're definitely understanding why we are only looking at one example.